Friends, welcome to the tutorial series on network analysis made simple. In this tutorial, we shall solve gate problems on basic circuit concepts. Hope you will enjoy the tutorial. Let's go ahead. Friends, now we shall solve the gate question from 2018. In this question, we are required to find the voltage Vc across the capacitor in the circuit shown in figure. Options are given and we have to identify the correct option. Friends, the given problem is straightforward and very simple. If you observe the given circuit, you find that two resistors of 100K are in series and their equivalent is 200K. So, incorporating this, the reduced diagram is shown here. We know the applied voltage V is equal to 5 sine 5t volts and it can be written as 5 sine 5t plus phi. Phi is the phase angle and here it is 0. So from the equation of the applied voltage, we get phi is equal to phi angle 0 volts and omega is equal to 5 radians per second. So once we know omega, we can find the capacitive reactance in ohms. It is very easy. We know minus jxc is equal to minus j into bracket 1 divided by omega c, and by substituting the values and solving we get minus jxc is equal to minus j 200k. Now once we know resistance and the capacitive reactance, the circuit is very simple. So straight away we can write the equation for Vc. So Vc is equal to phi angle 0 divided by 200k minus j200k. This is the current in the circuit multiplied by minus j200k, which is the capacitive reactance. So by solving this simple equation, we get Vc is equal to 3.535 angle 135. But the answer that we have obtained is to be brought into the form of the given options. So we see that 3.535 is 2.5 into root 2 and angle 135 is equal to minus 45 and that is equal to minus pi by 4 and 1 upon 4 is 0.25 and hence we get Vc is equal to 2.5 root 2 sine 5t minus 0.25 pi and hence option C is the correct answer. Very simple, isn't it? Friends, next we shall solve the question from GATE 2019. In this question, it states that in the circuit shown in figure, Vs is a square wave of period t with maximum and minimum values of 8 volts and minus 10 volts respectively. Assuming the diode is ideal and R1 is equal to R2 is equal to 50 ohm, we are required to find the average value of the output voltage VL in the circuit shown in figure. Now, to find the output voltage VL, the gist of the process is to find the status of the diode in the period of the applied voltage waveform considered. We should identify whether the diode is conducting or not. This is important. Further, you know that the diode is assumed to be ideal. So, when the diode is forward biased, it is short, and when the diode is reverse biased, it is open. So, if you know these two things, you can very easily solve the problem. Let's proceed ahead. You see that for the time period between 0 to t by 2, the input voltage is plus 8 volts. So Once the input voltage is plus 8 volts, you see that the diode is reverse biased and is open. So, by opening the diode, the circuit drawn is shown here. As a result of the diode being open, you find that the input voltage of 8 volts appears across the series combination of two resistances of 50 ohm. So, once you know this, you can straight away write the equation for the output voltage VL. So, VL is equal to 8 volts divided by 50 plus 50 into 50 is equal to 4 volts. It means for the period t between 0 to t by 2, the output voltage VL is equal to 4 volts. Next, during the second half, for t between t by 2 to t, Vh is equal to minus 10 volts. It means we have to reverse the polarity. So you see that the polarity is reversed here, and as a result you find that the diode is forward biased and it is short. So you see that in the figure shown the diode is short. Once the diode is short, this 50 ohm resistance is short circuited and hence it can be treated as open. Now, you see that the input voltage of 10 volts directly appears across the output voltage VL and hence VL is equal to minus 10 volts. So, incorporating these output voltage values, the the waveform drawn is shown in figure, and you see that for the time t between 0 to t by 2, the output voltage is plus 4 volts, and for the time t between t by 2 to t, the output voltage is minus 10 volts. So once you know this, you can very well easily find the uh, value of the average value of the output voltage, and we shall see in the next discussion. Friends, the problem statement and the circuit diagram given is shown here, and also the output waveform that we have obtained also is given here. You know, to find the average value, it is very simple. VL average is equal to 1 upon t into bracket integration 0 to t by 2 4 dt plus integration t by 2 to t minus 10 dt. By expanding the bracket, we get VL average is equal to 1 upon t into bracket integration 0 to t by 2 4 dt minus 1 upon t into integration t by 2 to t 10 dt. By integration, we get VL average is equal to 1 upon t 4t between the limit 0 to t by 2 minus 1 upon t into 10t between the limits t by 2 to t. By substituting the limits and solving, we get VL average is equal to minus 3 volts. Very simple and straightforward, isn't it? Friends, next we shall solve the gate question from 2014. In this question, it states that in the circuit shown in figure, the capacitor is initially uncharged, means Vc0 is equal to 0. And we are required to identify the expression describing the current I of t in milliamperes for t greater than 0 out of the given options. And if you look at the circuit given, the current which we want to find out is the current flowing through this 2K resistance. And capacitor and resistances are in parallel. So, Vc appears across 2K also. And we have to use the data given regarding Vc that you have to understand. So, it is given that the capacitor is initially uncharged, meaning it starts charging when the voltage is applied. So it follows the charging equation. What is charging equation of the capacitor? We know Vc of t is equal to V naught into bracket 1 minus e to the power of minus t by tau. So you see that when t is equal to 0, Vc0 is equal to 0 and Vc reaches maximum as t tends to infinity. So you know the voltage across the capacitor is also the voltage across 2K resistance, and because Vc is exponentially increasing function, the current that we want to find out also will be an increasing function, and hence I of t is equal to I naught into bracket 1 minus e to the power of minus t by tau, where I naught is the steady state current. So if we find I naught and the time constant tau of the circuit, our job is done. So you see that the current expression I naught is equal to Vc divided by 2K under steady state. And under steady state you see that the capacitor is open because the circuit is at steady state when t is equal to infinity, and at t is equal to infinity capacitor behaves as open circuit, and hence we shall open the capacitor. And now you see that I naught is equal to 5 volts divided by 1 plus 2 equal to 3K, and hence I naught is equal to 5 divided by 3 milliamperes. So once you find out I naught, and if you observe the options given, option B and option D can easily be eliminated because of the magnitude of the current is different there. Now what is left out? We have to find out tau, the time constant. So to find the time constant, you know that the energy storing element is to be open, so capacitor is open, and sources are to be made 0. Yes, 5 volt source also is made 0, and if you look into the circuit, that will give us R equivalent. And you see that 1K and 2K are in parallel, and hence R equivalent is equal to 1K parallel 2K, and R equivalent is equal to 2 divided by 3K. And tau is equal to R equivalent into C, and that is equal to 2 divided by 3K into 1 farad, which will give us tau is equal to 2 divided by 3 milliseconds. So we found out I of t is equal to 5 divided by 3 into bracket 1 minus e to the power of minus t by tau, and tau is equal to 2 divided by 3 milliseconds. And if you observe the options given, we find that option A is the correct answer. Friends, next we shall solve the gate problems of 2009. It states that an AC source of RMS voltage 20 volts with internal impedance Zi is equal to 1 plus J2 ohm feeds a load of ZL is equal to 7 plus J4 ohm shown in figure. We are required to find the reactive power consumed by the load, and the options are given, and we are required to identify the correct option. As a matter of fact, the problem is very simple. You know, reactive power consumed by load is the power consumed by the reactive component, that is XL in this case. And reactive power QXL is equal to IRMS squared into XL VAR. So the problem is this simple. You have to find out IRMS, voltage is given, and the impedance you know. So find IRMS and then find the reactive power using this equation. That is so simple. But I thought if we discuss little about the complex power and the components of the complex power, it will help you to solve such problems very easily. So, observe the power triangle. In this triangle, this component is true power and P is equal to V into I into cos phi, and it is measured in watts and kilowatts, that you know. The vertical component is a reactive power. It is represented by Q, and Q is equal to V into I into sin phi, and it is measured in VAR or kVAR. And this component is an apparent power and is denoted by S, and S is equal to V into I, and it is measured in volt amperes or kVA. Now, if we discuss different components of the complex power, it will be helpful. So, the apparent power is a combination of true power and reactive power, whereas true power is a result of the power consumed in the resistive components. Remember this, in the resistive components, true power is a power consumed in the resistive components. Whereas the reactive power is a power consumed by the inductive and or capacitive components. So, if you know this, such problems can be solved very easily. So, in our case, Q is equal to IRMS squared into X, and X may be XL or XC. But you know, true power is equal to IRMS squared into R, watts or kilowatts, and this power also is called as real power, active power, and average power. Whereas the complex sum of the real power P and the reactive power Q is known as complex power, and it is denoted by S, and S is equal to P plus JQ, and that is equal to IRMS squared into Z, and it is measured in VA or kVA. So, to find reactive power, let us first find IRMS. We know IRMS is equal to V divided by Zi plus ZL. By substituting, V is equal to 20 angle 0 and Zi is equal to 1 plus J2 and ZL is equal to 7 plus J4, and by solving we get the IRMS is equal to 2 angle minus 36.86. So, the reactive power Q is equal to 2 square into 4, which will give us 16 VAR, and hence option B is the correct answer. Very simple, isn't it? Friends, next we shall solve the question from GATE 2020. In this question, it is given that the current in RL circuit shown in figure is given, and I of t is equal to 10 cos 5t minus pi by 4 amperes, and we are required to find out the value of the inductance in henries. So, if you observe the given circuit and the given data, you find that the voltage applied is given, the current flowing through the circuit is given, so you can find out the impedance, which will be equal to R plus JXL, and the phase angle between the voltage and the current also is given. So using that, we can find the relation between R and L, because here both R and L are unknown. So we know phi is equal to 200 cos 5t, from which we get phi is equal to 200 angle 0 volts and omega is equal to 5 radians per second. And the current equation is given, I of t is equal to 10 cos 5t minus pi by 4, and I is equal to 10 amperes and phi is equal to pi by 4. But tan of pi by 4 is equal to 180 degrees divided by 4, and that is equal to 45 degrees, and hence tan pi by 4 is equal to 1. This important relation we can use it because we know tan phi is equal to omega L by R and we know omega 5. So by substituting we get the relation between R and L and hence we get R is equal to 5L. So once we get the relation between R and L, we can easily find L. So we know phi divided by I is equal to impedance Z and that is equal to R plus J omega L, and the magnitude of Z is equal to square root of R square plus omega square L square. So if you look at this term, we know omega and we know R in terms of L, and hence if we substitute we can find the value of L easily. So we see that we get 200 volts divided by 10 ampere is equal to square root of R square plus 5 square L square, and by substituting the value of R is equal to 5L, we get by solving this 50 L square is equal to 400 and L is equal to 2.83 Henries. Very simple and straightforward, isn't it? Friends, next we shall solve the question from GATE 2021. In this question, we are required to find the current I flowing through 7 ohm resistance connected between the nodes P and Q in the circuit shown in figure. You may feel that the network seems to be little complex, but it can be transformed into simpler network provided you know how to read the connectivity of the circuit elements in the given network. Further, you also should know that how to transform the given network into simpler network retaining the same connectivity. This is very important. So, if you observe the network, you find that the nodes A and B are short circuited and hence both the nodes will act as a single node. So, if you observe the connectivity of the resistances, you see that 3 ohm and 6 ohm are in parallel and 2 ohm and 2 ohm also are in parallel. So let us draw the reduced network. You find that the combination of 3 and 6 ohm in parallel is connected between P and A comma B in the original network, and in the reduced network also this combination is connected between P and A comma B. Similarly, the parallel combination of 2 ohm each is connected between Q and A comma B in the original network, and here also that parallel combination is connected between Q and A comma B. So let us now draw further reduced network. You see that again 3 parallel 6 is equivalent to 2 ohm connected between P and A comma B, and parallel combination of 2 ohm each is equal to 1 ohm, and that is connected between Q and A comma B. Further, you see that the current source of 5 amperes is connected between Q and A in the original network, and in both the reduced network you see that it is connected between Q and A comma B, number 1, and number 2, in the original network current of 5 amperes enters A comma B. So in both the reduced network the current of 5 ampere enters A and B. This is how you have to transform seems to be a complex network into very simple network. So now if you see the reduced network, you find that 2 ohm and 7 ohm are in series, and this series combination is in parallel with 1 ohm. And using the parallel branch theorem or current division theorem, we can find I flowing through 7 ohm very easily. So you see that current I is equal to 1 ohm, which is the resistance of the other branch, divided by sum of the resistances connected in the parallel combination, and that is equal to 1 plus 2 plus 7 into the total current 5 amperes, and by solving this we find that the current I is equal to 0.5 amperes. Very easy, isn't it? Friends, in this tutorial we solved the problems which evoke the basic concepts that you have learnt. Hope you enjoyed the presentation. Thank you for watching.